Okay, we at our second part of chapter 3. This part of the chapter deals with methods of proof that we use in discrete mathematics. Okay, now let's go through a few statements. I think it will be quite useful to know why these things are true and why they look the way they do. So it says you decide which of the following are valid proofs of the following statement. If AB is an even number, now AB, folks, means the product of A and B. It's not 21, A is 2 and B is 1. It's a product of two integers. Then A or B is even. If this is an even number, then A or B is even. Well, let's see. Suppose A and B are odd. That is, that A takes on that form. Now remember, every odd number takes on this particular form. This here is the form of an odd number. Okay? And you'll see the form repeats there. Twice something plus 1. Well, it's twice something because if it was only twice something, that number would be even. Why would it be even? Because all even numbers are multiples of 2 for some integer m. Okay, so suppose A and B are odd. That is, that A takes on that form, B takes on that form for some integers k and m. Then the product of the two would look like this. Now I've written here that it's valid. Now let's see why. If I distribute the two brackets, I get to 4km plus 2m plus 2k plus 1. Now if you look at the first three terms, I can remove a 2. So it has the same form. 2 times something plus 1. Okay? Now, is this valid? Is A and B then odd? So again, if A and B is an even number, AB is an even, the product of the two is even, then A or B is even. Okay? Therefore, in this case, A times B is odd. So A or B was even. Okay? Then A or B is even if the product is an even number. Sorry, if the product is an even number. So we said that we're assuming the product is odd, and we proved something about that. That indeed the product will be odd if both the numbers are odd. Okay? So the product is indeed odd. Number 2. Let's go down and see what this says. Assume that A or B is even. Say it is A. The case where B is even is identical. So we're going to assume that A is even. So A can be written in the form 2k for some integer k. Then AB is an even number multiplied by B. Okay? So we can put the k and the b together, we can distribute the b in and remove the 2 as a common factor. So that is even. That product is even. If one of its factors was even, so that's a valid argument. It is indeed even. The next one. Suppose that AB is even, but A and B are both odd. Okay? Namely, let's go down a bit. A and B is an even number, but A is odd and B is odd for some integers n, k and j. Now you brought in those, so you've got to define them properly. Okay? So suppose this product is even, but A and B are both odd, so they take on those two forms. Then let's see. If I multiply, if I want AB is 2n. I need to multiply that with that. I get to the same thing that I got to right at the top. Okay, so what does this tell me? It tells me if I can divide this by 2, this whole thing by 2, then I end up with n being 2 kj's plus k plus j plus a half. Now folks, since 2k plus j plus kj, 2kj plus k plus j is an integer, it's the sum of integers. That says that any integer n is equal to a non-integer, which is impossible. Okay? So the way we've proved it here is a valid proof. So what did we do here? We must think about what we did in each of these examples. The fourth and last example that he gives us is the following. He says, let a and b be an even number. Say ab therefore is n, and a be an odd number, so that's the form of the odd number. Then if we form the product, there we go, 2n. Now all of this is trying to prove that ab is an even number when a and b are both even. Okay? So here a be an odd number, so we say that that is the case. We multiply it with b, and we selectively regroup. We regroup these two together so we can remove the 2. So on the left-hand side of this equation, we will have an even number. And that would mean that b is even. So yes, one of a or b was even. Okay? So therefore b is even. Now folks, that represents the same problem. All of this was trying to show that if a and b is an even number, then either a or b will have to be even. All four of the ways we presented the argument are valid ways of arguing. I like what he's written on page 214. He says, writing proofs is a bit like an art. Like any art, to be truly great at it, you need some sort of inspiration, as well as some foundational technique. Just as musicians can learn proper fingering and painters can learn the proper way to hold a brush, we can look at the proper way to construct our arguments. It's a good place to start. A good place might be to start Okay, so let's look at the following theorem. There are infinitely many primes. That's all the theorem says. Okay, how are we going to prove this? Well, let's suppose that this were not the case. That would mean we suppose there are only a finite number of primes. Note the word suppose, okay? Or we could have used the word assume as well, but suppose makes perfect sense here. So this is what we call a premise. We are going to suppose that there are a finite number of primes. Okay, it's our premise. Then there must be a largest prime, which in this case we will call P. Now what does this mean? This follows directly from this line, that there is a finite number of primes. So if there's a finite number of primes, there definitely has to be a largest prime. Okay? So it follows directly from the first line. So now we're going to consider the number n, which is p factorial plus 1. Now if we take that number, the number is made up as follows. P times p minus 1 times p minus 2 continues in that fashion. That's what p factorial by definition means, until it hits 1. And then we add 1 to that result. Okay, so this is mainly notation that we're introducing, but it forms part of the inspired part of this proof. And that would be to look at what is p factorial plus 1. And that is our key insight. Okay, so let's have a look. Now n is certainly larger than p. Okay, by the way it has been defined. Okay, the number n, which is p factorial plus 1, is larger than the largest prime, which we called p, just by looking at its definition. Okay, so since every number less than or equal to p divides p factorial, why is that the case? Because that's by definition what p factorial is. Okay, so every number, let's read that again. Every number, since every number is less than or equal to p, it divides p factorial. It's because of the way we define p factorial. Okay, let's read on. Thus, the prime factorization of the number n contains the prime numbers, possibly just n itself, that are all greater than p. Let's read it again. The prime factorization of n contains prime numbers greater than p. That is what that line that's marked with a 6 is saying. Well, since n is divisible by each prime number in the prime factorization of n, and by line number 5. Okay? That's why this is true. Therefore, what does that mean to us? P is not the largest prime, which in this case is a contradiction. Why is P not the largest prime? Well, by line 6, n is divisible by a prime number larger than P. Look at this. Thus, the prime factorization of n contains prime numbers, possibly just n itself, or all greater than P. So P is not the largest prime. It produced a contradiction. Okay, therefore, there must be infinitely number of primes. Now this comes from a combination of line 1 and 8. Our only premise led to a contradiction. So the premise that we made was false. Suppose that this was not the case. Okay, so he says that this proof is an example of a proof by contradiction. One of the standard styles of mathematical proof. That's one of the styles we're going to study. First and foremost, the proof is an argument. It contains a sequence of statements, the last being the conclusion, which follows from all the previous statements. So the argument is valid, so the conclusion must be true if the premises are all true. Okay, we conclude. When you come across a proof in a textbook, folks, you really should make sure you understand what each line is saying and also why it is true. So it's not just a statement, the reason for the statement that you're making. Additionally, it is equally important to understand the overall structure of the notion of proof. Now we're going to look at a few of these, and we'll see that they appear quite often. They repeat themselves in the field of proof. Okay, we're going to look at 4 standard ways of proving. We've already considered the first one. The first one was a proof by contradiction. The first such a proof that he refers to is a direct proof. This is the simplest style of proof that you can find in from a logic perspective, obviously. Often all that is required is to prove something is systematic explanation of what everything means. So direct proofs are especially useful when proving implications. The general format to prove if P then Q is, you assume P. Explain, 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 and therefore If all those explanations and the assumption is true, therefore Q follows. Often we want to prove universal statements, perhaps of the form, for all P, Px, Qx. Px then Qx rather. Again, we will want to use or want to assume Px is true, and from that assumption, through various discussion points, deduce that Q will be true. But what about the x? We want to work for all x's. Must be a universal statement. We accomplish this by fixing x to an arbitrary element of the sort we are interested in. Okay, so we're going to do a few examples. First, we will set up the proof structure for the direct proof, and then we'll follow by filling in the details. Our first proof that we will focus on asks us to prove the following. For all integers n, if n is even, then n squared is even. Okay, so it's a universal statement. For all integers n, if n is even, so will n squared be even. Okay, so let's talk about the structure of the proof. We're going to have, first of all, an arbitrary number n that we will introduce. We're going to assume n is even, and therefore from that we're going to follow on to n squared is even. So that's the structure of the proof that we're going to be working with. Okay, to fill in the details here in between, we basically just explain what it means to be even. So that's very important. What does it mean to be even? It means it has to be a multiple of 2, then it's even. And then see what it means for n squared to be even. That will complete our proof. So here's our proof. We're going to introduce, let n be an arbitrary number or integer such that n is even. So it's an arbitrary integer such that it is an even number. Okay. Based on this, we can now say, therefore, n takes on the form 2k. So this is the form of an even number. Okay. For some integer, okay, remember we're working with discrete mathematics, so we're working with integers, whole numbers, natural numbers. Okay, now we've defined our n as even, we've said what it means to be even, and for which values of that integer k, or for which values of k will it be even. So now let's look at n squared. Well, n squared will be, by this definition, 2k squared. And that distributes to become 4k squared, which is twice 2k squared. So it still has the form of an even number. It's twice something. Okay? Do we agree with that, folks? Since 2k squared is an integer, we're squaring an integer and we're doubling it, so it remains an integer. Okay, so this then concludes the final part. Therefore, n squared is indeed an even number. Okay, and there we've proved it. This is a direct proof. That is what he calls a direct proof. Okay, our second proof we're going to focus on says that prove that for all integers a, b and c, if a divides b and b divides c, then a divides c. This symbol here, if I write x with a vertical bar y, it means x divides y. Okay, folks? Which means that usually then x is a multiple of y. X is a multiple of y. Okay, now that's what we're going to prove. Now let's first talk about the structure of what we're going to do. Okay, we can set up a direct proof clearly for this statement. It'll go something like this. Let a, b and c be arbitrary integers. So we'll define them as arbitrary integers. Then we're going to assume that a divides b, and also then that b divides c. So we're assuming a divides b and b divides c. Dot, 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 dot. And then we're going to work towards saying, therefore, a has to divide c. Now that's the structure of the proof. The reasoning is what is important. So the dot, 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 dot part is what I'm going to focus on now. We say that our hypothesis a divides b and b divides c really means what it means, and why this gives us the conclusion that a will divide c. Okay? And what that conclusion then means. Another way to say this is that to say that a divides b is to say that b is indeed a multiple of a. Then a will divide b. Okay? And we do the same for the b and the b dividing the c. Okay, so what do? What are we going for then? We're going for c being a multiple of a at the end of this whole exercise. So again, we want to work with b being a multiple of a. So we're going to write b as pa or ka or whatever for some integer kb, whatever we're going to use. What we are going for is to show that c is a multiple of a. Okay, so here's our proof. Let's define our variables. Let a, b and c be integers. Okay, so we're defining them as integers. Assume that a divides b and that b divides c. Now what does this assumption mean? It means that b is a multiple of a and c is a multiple of b. Now we're going to use those two and explicitly state what they mean. So, there exists k and j that are integers such that, remember that symbol, such that b is equal to k times a and c is equal to j times b. Okay, so we're saying c is a multiple of b and b is a multiple of a. By saying there exists k, j that are integers such that this is the case. So we've introduced them, we've made our assumption, and we also then continued to say what our assumption implies. Combining these now through substitution, so I want to get to a and c, so I need to get rid of b. So what am I going to do? I'm going to plug this here, my first statement is going to be plugged into number 2. Then I end up with ka, b, which is ka, times j, which is equal to c. Okay? j, ka, j, what did I do? I substituted B with Ka. So C is a multiple of A. Okay? Why can I say that? Well, but K and J are integers by themselves, so Kj is an integer by definition. And by the way, we've defined this. So C is a multiple of A. And therefore we can conclude finally that A does indeed divide C. And there's our direct proof. Now please folks, you need to know the structuring of your proof and the reasoning of the proof. Every proof has that as components. There's a structure to the proof and there's a reasoning component to that proof. And that reasoning component and the structural component together constructs a beautiful proof where statements follow onto each other and we draw a conclusion or a universal conclusion about what it is that we were to prove.